A ladder with a length of 5 meters is propped against a wall that is perpendicular to the ground. If the bottom of the ladder is pushed towards the wall at the rate of 2 meters per second at the instant the top of the ladder is at the height of 4 meters, find the rate at which the A, top of the ladder, slides along the wall, B, angle that the ladder makes with the ground changes, and C, angle that the ladder makes with the wall changes. We have a triangle here, so it's best to draw a picture of it. We have a ladder leaning up against a wall that is itself perpendicular to the ground. The length of the ladder is a constant, so we can label the constant on the picture. It will be the 5 meters hypotenuse. The bottom of the ladder is being pushed towards the wall, so that side of the triangle is going to change. Let's label that as X. As the bottom is pushed towards the wall, the top of the ladder will itself slide along the wall, so that side will also change. Let's label that as Y. Since the bottom of the ladder is being pushed towards the wall, the X will be decreasing. So the rate of change of X, X prime, or dx dt will be a negative number, and the rate given to us is 2 meters per second, the rate at which it's being pushed towards the wall. We are also given the height of the top of the ladder. That will be the Y value. Y equals to 4 meters. For part A, we're looking for the rate at which the top of the ladder slides along the wall. The top of the ladder is measured in a height by Y, so we're looking for the rate at which Y changes. We have the rate with which X changes, and we want to find the rate with which Y changes, so we have to relate Y to X. X is the length of the bottom of the triangle, Y is the length of the vertical side of the triangle. They're related to each other by the Pythagorean theorem, since they're legs of a right triangle. So we can write down that one leg squared plus the other leg squared equals the hypotenuse, which is a constant, 5 squared. There's our related variables equation. From this, we can produce the related rates equation by taking the time derivative of both sides, indicated by a prime on both sides. Every variable is implicit with time, so when we take the derivative, every variable will get a prime due to the chain rule because of implicit differentiation. So the first term, x squared, will be a power rule. Bring the power down, subtract 1 from it, and then multiply by the derivative of the inside to complete the chain rule. There's the x prime for that one. The second term is a power rule. Bring down the power, subtract 1 from it, then multiply by the derivative of the inside. There's the prime for that one. On the right side, we have the derivative of a 5 squared, which is a constant. The derivative of a constant is 0. Since we're equal to 0, we can divide both sides by 2, and the 2's will cancel. We're trying to solve for y prime here. We need x, x prime, and y to be able to do that. We have x prime, we have y. We do not yet have an x. But x and y are related to each other by the related variables equation up here, so if we know y, we can plug it in and find x. Let's do that. I'm going to do that calculation down here by the picture. So x squared plus y squared equals 5 squared. X squared plus 4 squared equals 5 squared. X squared plus 16 equals 25 if we square each of the numbers. And now we can subtract 16 from both sides, so x squared equals to 9. And then take the square root. We will get positive 3 as well as negative 3, but this is supposed to measure the distance of the bottom of the ladder to the wall. It cannot be a negative number, so we will only keep the positive number. We're in length units here of meters, so that'll be 3 meters. We can now plug that 3 in for x up here in the related rates equation. 3 times x prime, which is a negative 2, plus y, which is a 4, times y prime equals to 0. So negative 6 plus 4y prime equals to 0. 4y prime equals to 6 if we add 6 to both sides. And y prime will be 6 over 4, or reducing 3/2. So y prime, or dy dt, will be 3/2 units of y, which is measured in length in meters, over time, which is measured in seconds, meters per second. Since we have a positive number, that's indicating that y is becoming longer, so apparently it's sliding the top part of the ladder up the wall. For part B, we want to look for the rate at which the angle that the ladder makes with the ground changes. On the picture, it's this angle. I will name it theta. We now need to relate theta to one of the variables that we know the rate for. We know the rate for x, that was given, and we just found the rate for y, so we can use either one of those. It's best to also use the constant, which turns out to be the hypotenuse on this triangle. So I'm going to use cosine of theta because that will be equal to the adjacent side, which is x, over the hypotenuse, which is a 5. Cosine of theta equals adjacent side over hypotenuse, so x divided by 5. That's the related variables equation. We can find the related rates equation by taking the time derivative of both sides, indicated by a prime on both sides. On the left side, the derivative of cosine is negative sine, leave the inside alone, but then multiply by the derivative of the inside, which is theta prime, to complete the chain rule. On the right side, no need for a quotient rule because the denominator is a constant. We just take the derivative of the numerator. The derivative of 1x is 1, but then times x prime due to the chain rule because every variable will have a prime due to the implicit derivative with time. And it just ends up over the 5. We can now plug numbers in. We have the negative sine of theta. Now sine of theta, if we look at the triangle, will be the opposite over the hypotenuse. The opposite is y, and we know a y value, that's a 4, and the hypotenuse is a 5. So the sine of theta is just 4 over 5, and there's a negative in front of it. Theta prime is what we're trying to find out. X prime was given to us, and that's a negative 2 over 5. We can now cancel the 5's out as long as they're in the same position on opposite sides of the equal sign. They can be canceled. And so theta prime becomes, dividing both sides by negative 4, negative 2 over negative 4. We can cancel the negatives and we can divide both by a 2, which will reduce to a 1/2. So theta prime, or d theta dt, equals to 1/2. The units on this are the units of an angle, radians, over time, which are time units in this problem, or seconds, radians per second. For part C, we want to find the angle that the ladder makes with the wall, what rate that changes with. If we go back to the picture, I can name that angle, say, phi. It's that angle there on the triangle. Now again, we can use a trig function, or another option, now that we've found the rate of theta, the theta prime that we just found in part B. We can relate phi and theta through a more simplified formula, because theta plus phi plus the 90-degree angle total up to be 180 degrees, because that is what comprises the entire triangle here. And we can now Subtract 90 degrees from both sides, and we have theta plus phi equals 180 minus 90, which will just be 90. And there's our related variables equation. We can now take the derivative of both sides, indicated by a prime on both sides. On the left side, the derivative of theta is 1 theta prime. The derivative of phi is 1 phi prime. Again, every variable is implicit with time, and we'll get a prime on it. Equals to the derivative of a constant 90 degrees is 0. And now we can plug numbers in. We just found theta prime to be a 1/2, and we're solving for phi prime, and it looks like phi prime comes out to be just the opposite sign of whatever theta prime was. By subtracting the 1/2 over, we get negative 1/2. So phi prime, or d phi dt, equals to negative 1/2. Again, it's angle units radians over time units seconds, radians per second.